First, we have Chris McCubbin, our Director of Data Science at Squirrel, talking about performance models for Apache Accumulo.
Thanks, Eli. Like Eli said, I'm the Director of Data Science at Squirrel. I'm a co-founder, so I've been around a bit. Mostly my tasks are to do like graph analytics, proof of concepts, prototypes, that kind of thing. But occasionally I'm called on to improve the performance of some of the core components of our product. So this talk today is about one of those stories. You can kind of view it as a case study, but I have some kind of lessons learned, some takeaways. So for Accumulo in general, and maybe just applications in Accumulo too. So I have a quick intro to maybe sort of general performance optimization. Most people should know a lot of this stuff. So then we're going to move into techniques for targeted distributed application modeling and performance enhancement. I'm going to take a deep dive into improving one particular task that we do a lot in Squirrel, so bulk load application performance, and a shallow dive, I guess that's like snorkeling or something, I don't know, into partial schemas. We'll talk a little bit about that. So your application's slow. That's too bad. I don't know. What are you going to do about it, right? So it's hard. Today's applications run on maybe tens or even hundreds of library components that you don't know who coded them. You don't really want to look at that source. There's many versions out there. So Hadoop, right? Everybody uses Hadoop here. There's probably in the wild at least 10 versions of Hadoop or more. So if you look on the internet, a favorite IT task, Google, you're going to get advice, and that advice might be ineffective. It might be for a previous version. Worse, it could be flat out wrong. Like you might get advice, you might do it, and it makes your application slower. So because of changes in the underlying libraries. These things have hundreds of settings. Not particularly user-friendly, some of these libraries, and a little bit short on documentation because, nobody likes to write that stuff. Things like shared nothing architectures like Accumulo usually aren't truly shared nothing, right? They share a little. Otherwise, they can't really do anything. And understanding those interactions is difficult. You have to know exactly what's going on. And that could be the source of a lot of the problems. And profiling, you could just say, okay, profile your app. That's great if you're single-threaded. That's great if you have a good profiler. But in these cases, so I'm going to talk about MapReduce, right? Profiling MapReduce applications is not easy, just practically. So mappers start up, reducers start up, they go away. Yarn's happening, things are happening behind your back. Attaching profilers to those things and analyzing the results, not easy, at least in my experience. So maybe full screen here? Or is this okay? Can you guys see that? So, kind of the first step, we go back to Google, right? We find out the best practices, common knowledge. Like I said before, maybe this is wrong, but, it's a good place to start. You might use your network too much. Network is definitely a bottleneck. You have maybe, I don't know, Ethernet, or maybe you have twisted pair. I don't know what you have, but there's a limit to how many bits you can push over that wire. So that's a good place to start. It's definitely slower than memory or disk. You might be disk bound. So if you're writing a lot of stuff to disk, maybe that's a good place to look. Disk is obviously much slower than memory. So it's sort of common knowledge here that in MapReduce Job, especially straggler tasks that, maybe you have 100 tasks and 99 of them finish in 10 seconds, the last one takes an hour. So that's going to push your time to up to an hour because of that one guy. So what's that one guy doing? So stragglers are often cited as a source of issues. Your framework settings, like I was saying, Hadoop has 50 million settings. We just saw a talk about how one setting can improve your performance by 50% if you turn on one setting. So there's all these other settings too. How do you tune those things? Unbalanced distribution, so maybe Hadoop promises that your data is distributed throughout the cluster effectively. Do we really believe that? I don't know. Sometimes more data is in one place than another because of maybe what you did. And lastly, serialization and deserialization, SERDI. So serialization is expensive, especially nowadays with the types of serialization that we do, gzip, other things like that. Those things would be very computationally intensive, or even custom SERDI. So that's a lot of places to start. What do we do first? Like, we got to do something first. What we want to do, and I'll mention Amdahl's law later, is we want to hit the one part of our system that's taking the most time and that has the most potential for improvement. So how do we do that? Especially in the cases where, my cluster is not your cluster, my app's not your app. So the usual suspects are great for the usual case, which is none. There's no usual case. So what do we do now? So I'm going to advocate, kind of this performance analysis cycle. In the beginning, you make a model of what your application's doing. It might be bad. Use what use common knowledge, things like that. And the kind of key part here is, you simulate that model, do experiments, try to analyze and see if your model is a good model. From that model, do the analysis, pick out the parts that look most promising, modify your code, refine your model. That's another important part. You say you made some assumptions in the model. They might be wrong. Refine that model and keep going around this loop. And kind of as the output of this model, right, you're going to improve things. You'll hit the most, the hardest part of the algorithm. You'll improve that part. When you do that, Amdahl's law says when you make that go away, something else is going to be popping up. So that's the next thing you focused on. And you kind of keep going around in this model. You have a model of your system. At the end, you'll have better code. And awesome models, too, right? Those are always good because later on, when you change your code, inevitably, you can go back to that model and make sure it's still valid. You can use it for further improvement. So the models themselves are an output of this process. So how do you do this? One way is kind of, I'll advocate metric-driven modeling. You can make as many cool graph models as you want of your system. So if it's not observable, right, that doesn't really matter. It's not going to help you because you can't see what's going on unless you can directly infer it from something else. So kind of take stock. What can you see in your system and build your models around what you can see or what you can add without causing too much performance difference from the real system. And we like to create sort of parallel state machine models, things that look like graph models with flows. Data goes into the nodes, data comes out of the nodes. In a lot of these distributed applications, that's the way these things are built, so that's the way we're going to model them. So we want to estimate running times, stuff a priori. For example, that your twisted pair can handle 1 megabit per second, where if you're a normal person, you have gigabit Ethernet maybe. So you can tell if something's going over the network, that's as fast as it can go, and you're not going to get above that. And you can say okay, we know that this part is capped at this amount. So you can put that in there. And, run the model, do the simulations, put the numbers in, then focus on the pain points. Amdahl's law, right, which means if 20% of your time is spent doing something, right, if you make that go away, you still have 80% left. So if you determine that, something that you thought was bad is only taking up 1% of the time, you could spend hundreds of hours on it and you're not going to improve your application much. You have to focus on the things that make a difference. So this is the Accumulo summit. So I have a couple slides in here about Accumulo, but I think I'm going to go through this pretty quickly. Accumulo, it's a sorted distributed key value store. You can kind of view it as a giant hash map, right? Giant distributed hash map. So it has some good parts, I heard. This slide I stole from Adam, so you can blame him. But the way that Accumulo is set up, so we have tables. Tables are like logical sets of key values. Those tables are indexed by a metadata table and broken into tablets. And tablets are chunks of bytes that are stored in Hadoop, HDFS. Those tablets are also, the metadata tablets are indexed by a root tablet, and that's stored in the Zookeeper. So I think most of you guys know that. One of the, Accumulo pretty much supports two main mechanisms for bringing in data: streaming ingest and bulk ingest. So streaming ingest is your writer API. You write a particular key value pair, and it goes in and it's there. Bulk ingest has a little bit different goals. You want to maximize throughput, most key values per second, right? You don't care about latency here. It can take 10 minutes for that key value to show up in the database. You don't care as long as your key values per second is high, right? That's what you want. And the way that we support this is that Accumulo, you can create these tablet files, these RFiles. You can write them yourself using whatever means you want, right? And then you register those files with Accumulo. You say, Accumulo, here's some valid RFiles that I made. Load them in. So RFiles, groups of sorted key value pairs. They have to be sorted. They have some indexing information. There's writers that you can use to create them. But a really good thing is, MapReduce has a built-in sorting phase, right? In the middle between map and reduce, it sorts. So one of the easiest ways to create RFiles is to just emit all the keys that you want to create from map, let MapReduce sort them, and then have reduce write them out with a Accumulo RFile writer output format, and then load them in. So we have our model here. We have our map. Our map makes our keys from some input data, sorts, sends to reduce. Reduce writes out the RFiles to HDFS as sequence files, I think. And then you register them with Accumulo. And then Accumulo starts serving them as tables, right? So this is a pretty coarse model. We can't really do much with this. So this is kind of first order model. You can run your MapReduce job to create your bulk ingest data. And you can say in this hypothetical situation, I saw the mappers kind of pegging the CPU when I did top. Didn't really look like it was hitting the disk, even though map really is like writing to disk when it does the sort. It took this amount of time. Reduce took this amount of time. So what is this telling me? It doesn't really tell me much, because why is reduce taking a long time here? We don't have enough insight. So we're going to take this first order model that you get kind of just from timing things and looking at your top, essentially, and make it a little bit more granular. So if you look inside MapReduce, map and reduce have all these steps. So there's setup and sort of read, right? The things that you get your input data from. There's map, your map function that you use to take whatever you're reading in and write out key value pairs. That's immediately sorted inside the map thread and then written to disk in little teeny sorted files. Those things are merged together for one mapper. So if you make more than one spill, those things are merged together in a merge sort to make a bigger file. And then those things are served up to Yarn or whatever application system you're using. At that point, there's a parallel latch. Like, reduce really can't start until all the mappers are done, right? It can start a little bit, but really to get started, reduce needs to know all the things because it has to have its input sorted. And you can't sort the input until you know all the output of map, right? So after map creates these medium-sized files and sends them over the network to the reducer that's going to handle them, they're shuffled and sorted together again with another merge sort, and it runs your reducer function and then writes out to disk. So we have all these stages that are kind of, they're done. And they're not done in parallel for each individual mapper. A whole bunch of mappers run at once, and a whole bunch of reducers run at once. There's this latch in between, but inside each mapper, it's a linear process. So we can make some predictions here. We know how fast disk to memory is from HDFS. This is HDFS disk. We know how fast memory to disk is, disk to disk, network. And we sort of know how fast our algorithms of map and reduce run. And we know a little bit about SERDI, although SERDI is a little bit hidden in here, although it'll turn out that SERDI is a bit more important than we thought. So we have a model here. We can create these things that sort of flow through a network. We know how much is going in. We know how much is coming out. We can measure that using MapReduce's, the output, and I'll show that here. So MapReduce actually outputs a lot of stuff, right? It has what it's on the page that you see, but it also has a ton of logs. It tells you exactly like how much stuff is coming in, how much stuff is going out, the number of key value pairs, how long it took. I don't even know what else is in here. So we can calculate some things from this, like how much our data is being inflated, how long it took for a particular section, like serialization, deserialization, shuffle, sort. We have all these numbers for free from MapReduce, so we're going to use them. So we took that performance measurement, put it back into our flow model, and we find out that sort and spill, sort is bad in both map and reduce. Spill is also bad. So bad meaning it takes longer than we thought it was going to take given our a priori assumptions. So I call this a naive implementation. This is just us sending out keys that we want to ingest into our tables, and then just letting MapReduce sort them and write out to Accumulo. So given that, we do some focused profiling on just those parts, right? Profiling, like I said, is hard, but we're going to focus it just on these parts because we don't want to like sort of disturb the rest of the system by just like profiling everything. Profiling adds a lot of overhead to processes. It can mask certain things. So once we know something in sort is happening, we can profile just sort. So it reveals that a lot of time is spent serializing and deserializing Accumulo's key class. And kind of this idea that SERDI is a big deal, right, is supported. Like I just saw this last week and added it. There's a recent investigation on Spark jobs using some benchmark that as much as half of the CPU time used in a Spark job is spent deserializing and decompressing data. So that's a lot, right? Half. And these are in graph algorithms and stuff like that, so you would expect it not to be that high. So they were in that paper, you can go read it, they pretty much say disk bottlenecks don't matter, network bottlenecks don't matter. The only thing that matters in these benchmarks was serialization, deserialization. Once you take care of that, disk starts to matter again. So if you look deeper into MapReduce, with the proper configuration, MapReduce supports comparison of MapReduce keys. So this is in general, not just in Accumulo. It can support comparison and sorting of keys without deserializing them. So what happens normally is you pass it a key, it's comparable. Right out of map, the key is serialized. And then before it's even sorted, it's deserialized again. So it does a serialize, deserialize before it even leaves map. So if that costs a lot, you're hosed because like it does this on every single emission from the map function. What you can have it set up to do is have map and reduce compare keys in serialized form directly. That means the byte array that you make from serialization. So if there's a way that you can make your keys sort the same way serialized in terms of like lexicographic byte ordering as you sort them, in the normal way with your comparator, you can have a huge win here because MapReduce supports that comparison and it has sort of native byte implementations of that comparison function. You just say, use the fast byte comparator and just do that. So we also want to like tweak the input size and spill memory for as few spills as possible. So this is sort of the spill part. Spilling is expensive as writes to disk. We found out that you want to spill as little per key as possible. So you can tweak your map input size, the number of mappers. Spilling is really expensive, so you don't want to do it as little as possible. So once we made those two changes, it improved performance 3x just from SERDI and spilling. Okay, so that's a lot. So once you do that, like those other guys were saying, disk binding becomes a problem. So you took care of SerDes. SerDes is fine now. You have more CPU. We're going to profile again, run our numbers through our model. The intermediate data inflation ratio is high in our case, so we were, per thing coming into map, we were producing, multiple things. And it turns out then the mapper is then disk bound because we're writing a lot of stuff out of the mapper. But we can see that reduce is also disk bound. We couldn't really get away from that. We're sort of bound on both sides here at the ends. We have a particular thing we're inputting. We have a particular thing that we want to output. We can't change that. So reduce must output, a certain amount of stuff. It's fixed. So it's disk bound there, right? We can't really help that. So what we can do is, since map is also disk bound, if we can find a way to move processing from map into reduce, emit less from map, and have it be more expensive in the CPU side of reduce, then we're going to get a win here because reduce is already waiting on disk all the time. So it has extra CPU. So can we trade disk time in map for free CPU time reduce? The answer is yes. And we do that by reducing the inefficiency in transmission of data from map to reduce. So we want to emit less keys, we want to emit smaller keys, and by doing that, we write less to disk, right? So for example, in the Accumulo key, if we were going to emit a bunch of keys, we had a bunch of keys that were emitted from one map that move as a block to the reducer. That's really inefficient, right? A block meaning no other keys can kind of get in the middle, okay? So we have a constant timestamp, 8 bytes per key. You wouldn't think that's that big of a deal, but 8 bytes per key when you have billions of keys adds up. Repeated column names also, so column families, column qualifiers, if they're repeated, if they move as a block, you can get rid of them by just encoding them, right? So you can also do something like, if you have multiple values that go to the same key, what you can do is create a dehydrated key by just emitting one key, some metadata information, and those values that are encoded in a byte array. So it's dehydrated in that all your sort of schema information is encoded and known ahead of time, so the reducer can deserialize that. And we already know deserialization is expensive, but in this case, we're disk bound again, so we want to get rid of disk writes. So fewer keys and shuffle means the sort phase is also more efficient because you're sorting less things, right? So after we do these things, after the 3x improvement, we get another 2x improvement on top of that. And the reduced intermediate inflation sped up all the steps between map and reduce. So that's what we predicted, and that's what actually happened. So altogether, and maybe with some other minor improvements, we achieved a 6x speed up on our bulk ingest speeds, 6 times. So the takeaways here, perform comparisons on serialized objects and watch your SerDes, because it's hidden in most cases. You don't really see it, and it could be killing you. With MapReduce, calculate how many merge steps are needed. You want to reduce that if possible. Avoid premature data inflation. Inflate in the reducer if you are disk bound, right, in the reducer. And leverage compression and shift the bottlenecks around to where you have free CPU. And always think about, could I be writing this code faster, right? My code's only running at 10 megas a second. I think it can run at 100, so use that model to measure performance.
Quick question.
Sure.
The compression, it takes time to do this.
Yeah, so that's kind of what I was saying. You burn CPU time to allow for less disk time if you're disk bound in that part of the process.
And also, what kind of scheme? What scheme do you use?
So yeah, I don't think I really have time to talk about that too much, but I have a couple slides right on this. So yeah, I can go into that. The question was, what's the encoding scheme for the dehydrated keys? Was that it? Yeah. I'll talk about that for a couple slides, actually. So this is kind of our postscript. This is our shallow dive, and this is kind of getting away from models a little bit. But like we were saying, we have dehydrated compressed keys going from map to reduce. Wouldn't it be great if we didn't even have to rehydrate those keys, if we just sent them out to the files and stored those dehydrated keys as the values in Accumulo? So that makes our bulk ingest fast, makes our disk footprint of our R files smaller because we're not storing extraneous information, potentially faster query response because we have less keys. So there's some issues here. We need to keep the schemas around, right? So if we strip off all the schemas, essentially the document fields that we were storing before, and just keep the values, we have to know what those fields were in somewhere so we can get it back, right? How do you handle like these lazy updates that Accumulo is so famous for and that we love so much? It's hard. It's a little bit harder to do a lazy update. Say you have like 50 fields stored in one key and you want to update one of them. So that's a challenge. The documents need to be rehydrated sometime, so I want to get field 10 from my data. How do you get it out? And what's the perf trade-off there? So maybe we should do some more models, but that's the source of another talk, I think. So really, like, I'll talk a little bit about the schemas here. Really, we're keeping a key, the name of the document, an identifier that holds a pointer to the schema, and the compressed version of all the values. So to rehydrate this thing, you look up the schema, and you, for whatever values you have, you can say it's typed or whatever. Say the 10th value is this field, and then you read it off of the bits. So that's about all I had today. If there are any questions. So the comment was that you're trying to do a match on a particular field that had an enum of maybe hundreds of strings, and you reduced it to one character instead of a string. Yeah, so sort of in general, string comparison and byte comparison is very expensive, right? Like if you can get away with integer comparison or single byte comparison instead of string comparison, in Java it's just not very good at those kind of things. Sort of in general. So we see all the time when we have to compare strings, that's one of the slowest parts of the app. So the question is, can you do real-time streaming ingest at the same time as bulk ingest? Yeah, absolutely. So what happens there is, when you're streaming ingest, kind of the model is you build up a R file in memory, that's the log structure merge tree, and then write it out to disk when it reaches a certain size. So all that happens here is that the bulk ingest just brings another tablet online in bulk, right? A whole tablet at once, and the Accumulo's reader, like so on the query side, it looks to that reader that it's exactly the same as if a tablet just appeared out of nowhere. So it can, when you're doing the scan, what happens is it merges tablets together anyway, since you probably had a bunch of tablets writing out during streaming ingest, and it just adds that into the list of things that it's merging for the read. Eventually, those things will be minor or major, or they'll be major compacted into bigger files, and it just handles it like it's nothing. So, yep, you can do it. Yeah, so that's I kind of alluded to that the reducer is disk bound when it's writing our files. Yeah, I think there is quite a bit of room for improvement in that part of the process. We didn't really want to change Accumulo per se, like for this exercise, but I think writing out our files is definitely ripe for more performance enhancement. Yeah, definitely. Oh yeah, so one of the things that we did do is Accumulo writes R files compressed and maybe encrypted. So the settings of your compression or encryption have a large impact on the write performance. So if you're using nothing, right, if you're using no encryption at all, it's going to write unencrypted, and maybe a large file. If you turn on the built-in gzip compression, that'll write a much smaller file, but there's a much higher cost in CPU. And there's sort of a middle ground called with snappy encryption, so you can enable that if you have that downloaded and all that. That is not as good compression as gzip, but much, much faster. So what you kind of want to do is balance that. So if you know that you're disk bound, maybe you can turn on gzip compression and use more CPU and be less disk bound. There's also ways to, and there's a ticket about this in Accumulo, like if you can write files in a certain way, a certain compression during, say, bulk ingest, and then later on gzip them. So say I wanted to write it with snappy and then gzip them later. You can actually use Accumulo's compaction strategies to have that kind of compaction strategy. You can change things from snappy to gzip. And that way, if your load's disk bound, you can write it out quickly, but then later on reduce your disk footprint and when you have like more CPU available. Questions? Thank you.